So hello everyone, welcome back to the another lecture. So in this particular lecture we will talk about efficiency of non-ideal buck converter. So this is a general question that if all parasitics are considered in any converter, any DC to DC converter, then what expression we will get for the efficiency, right? So my name is Ashish and in this video we will talk about efficiency of non-ideal buck converter. So here I am going to consider all the parasitics like you can see the figure below that I have my DC voltage supply, then I have my switch, and switch has a on state resistance. My diode is there, diode has a forward voltage drop as well as its resistance. Then my inductor is there, inductor parasitics RL is there. I have capacitor is there, output capacitance have the parasitic RC is there, and my load resistance. Okay, so now we will derive the efficiency of the non-ideal buck converter step by step, how you can approach. I will recommend you, if you watch this video and learn how to basically design and derive the expression for non-ideal buck converter, you try yourself for the boost converter, then you will understand concept that how you can approach the things, right? So this is my circuit. Now I will go one by one. So first step is my mode 1. In mode 1 from 0 to dt, like when switch is turn on, what will going to be happen when switch is turn on? What is this particular branch will be my off, right? This particular branch will not be there. When my switch is on, this particular branch will be off, right? This is not there, so my circuit path will be like this, right? So my circuit path will be like this. Okay, so this is my circuit path. Now if I apply a simple KVL here, so what is going to be happen? I am going to write it down my inductor voltage expression. So VL of on of t, that is when the switch is on, that is why I have write it down on of t, which is equivalent to the L dIL by dt. What is the expression? Expression is Vg minus these two resistance drop, and current flowing through this is same at this particular time. Ig and IL both are same, so I have write it down IL minus my V naught, right? Minus my V naught. So V naught is there. So right now I have write it down V naught. V naught and this particular drop is same, right? But I will not say that V naught equal to Vc because RC is involved now, and if RC is there I cannot directly say that, right? So this thing you know. Now this is my expression when the switch is on, right? For the VL, same kind of expression I can write for the IC. So what is my IC? IC is a combination of IL and I naught. So IC current, if you see here, you can find out that what is my IC current. IC current flows here. So IC current is basically the current flowing through this branch, IL minus the current flowing in the output, IL minus I naught. And what is my I naught? I naught is V naught by R, right? I naught is V naught by R. That is why I come up with this expression. Okay, so now next thing we will see what is the next thing. So next thing is about this particular concept. So the next thing is my, what is my expression for the V naught? V naught is what? So same circuit is here I have drawn. So V naught is what? V naught is basically, if you apply the one KVL here, so you will come to know that V naught is equal to Vc plus RCIC. Vc plus RCIC is my V naught, right? So this is the expression for V naught. So I am come up to this particular point when switch is on. For mode number 1 I have write it down the three expression, right? For VL on, IC on and V on. Okay, output of on. So this expression I am getting. Now I am in my mode number 2. When I am is in my mode number 2, what is going to be happen? This particular switch is off. Now my circuit is only up to this. My circuit is this much, right? So I will apply KVL KCL here only, right? So now I will apply the KVL KCL and we will get the expression. The same kind of expression I am expecting. Okay, so just see. So talking about the mode number 2, I have told you that my current will flow only in this particular branch, right? In mode number 2. So I am writing down the inductor voltage equation first. So what is my inductor expression? Inductor expression is again L dIL by dt. This drop along with which drop? I have my RL drop, I have my RD drop. Two drops and current is same. IL current I can take, or ID IL both are same at this time. So I have write it down IL. Then my this forward voltage drop of the diode and my V naught, right? So this is my expression for VL off. Similarly, I have my expression for capacitor current. So what is capacitor current? Again, capacitor current is a combination of two things. One is the current flowing here minus my current I naught. So if I'll do that, I am going to get IC is equals to the IL minus V naught of T by R, right? Then another expression is my V naught output when the switch is off. So what is that particular expression? Again the same thing, VC plus RCIC. Simple KVL I am applying, I am going to get expression. So I have calculated my total 6 expression as of now. So first one is a inductor voltage expression when switch is on as well as switch is on. Capacitor current expression when switch is on, switch is off. Similarly, output expression when switch is on and switch is off. Now what we will going to do, now I am applying my inductor volt second balance expression. What is the inductor volt second balance? Say VL equal to basically average value of the inductor voltage over a one complete cycle equals to the 0. So I have just what I have to do, D into VL when the on and 1 minus D into VL when off. So if I do this, that I am going to get as 0. So I have just this expression, using this expression I have just substituted the value. So simply the above expression which I am getting, I have just substituted the value here, and once I have substituted the value, I have come up with this expression. Okay, I just rearrange the expression, what I am going to get. So this particular expression I am getting. So D into Vg equal to D dash. D dash here is a 1 minus D. Okay, so this expression I am getting here. Now another expression I am going to use, that is a capacitor charge balance. So what is the capacitor charge balance? Say average and capacitor current over a one particular cycle should be equals to 0, right? So just I have derived this expression, IC on, IC off, and I just multiplied with the D and 1 minus D. So I have just substituted the value, and when I rearrange it, what I am going to get, that IL equals to V naught by R, that is equal to I naught. So I come to know that my IL and I naught will remain same throughout the cycle. My IL and I naught will be same throughout the cycle. So average value of the IL and average value of the I naught will be same. So this is the concept. Okay, so this is which we have derived. I am not saying directly, we have derived it and we have come up with this. Third thing I am going to do is that the average and output voltage of the buck converter is basically how we will given it, D into V on plus 1 minus D into the V off of T. So if I have derived this V output when on and output when off, we have these two expressions right with us. So I am just substituted the value, and when I simplified this, what I am going to get is that V naught equal to Vc plus RCIC. But what I know, average value of the capacitor current over a cycle equals to 0. So that is what I am saying, that V naught equal to Vc. I am going to say here is that V naught equals to Vc. So this expression I am getting here, V naught equal to Vc over a one particular cycle. So V naught equal to Vc nearby I am going to get, because my IC equals to 0 over a one particular cycle. Now what I am going to do is that I am substituting the few equation here and there, like I am using this expression. This expression I am going to use, and I am substituting the values, and once I use this expression and substituted the value, I am come up with this expression. So this is the output expression for me. Okay, so this is very important expression. So V naught equal to D into the Vg minus D dash into the Vf whole divided by some denominator is there. So this is the output voltage expression for me when it is a buck converter, when considering all the non-idealities, right? Where D dash is my 1 minus D. Also, if I rearrange this expression, I am come up with the D expression. So D ideal. So what is my duty ratio expression? This is we are coming up with. So this is also very important expression. So you should know this expression. So you see here one thing as this is my D. This is a practical D. And what is my D ideal? D ideal is simply V naught by Vg. You know this expression for ideal buck converter, V naught by Vg is my duty ratio. So what is the expression for the duty ratio when all non-idealities are considered? So D is equal to D ideal into whole this thing is coming up. So it is not very simple expression because all the non-idealities are considered. Now from this I can derive the expression for the efficiency. So what is the formula for the efficiency? Efficiency is my V naught I naught divided by the Vg into Ig. So I can say that I naught is basically V naught by R. What is my Ig? Ig, when switch is on, only at that time my inductor current is the input current, right? That is why I have said, I have write it down here that Ig is equal to D into IL. Okay, and from this I have just calculated few things, and I can directly here what I can do is that I can cancel I naught and I naught here, right? I naught and IL are same, and what I am coming up with V naught by Vg is my D, that is D ideal, and same thing I have done here. Okay, so just cancel out few things, so you will come up with D ideal by D as my efficiency expression for the my idea for my practical buck converter. So this is the final expression which we are very much interested in, and this video is about the how to derive the expression for the buck converter. So I hope so you understood the step by step procedure that how you can proceed to derive the efficiency expression. So in the next lecture I will talk about maybe boost converter efficiency expression. So I want you, if you really wanted me to present the video, so you just comment out in the comment box so that I can get motivation and I will upload the video. Or you tried by yourself, and if you are facing any doubt you will just comment. I will try to answer your question, and maybe you will come up with proper output expression for the boost converter, also efficiency expression. So with this I will end up this lecture. So thank you, thanks for watching. So thanks.